Let's work some improper integrals that have infinities at the limits, and let's hope that we have enough board space to work on. So we want to just evaluate some integrals, and then we want to talk about whether those integrals are convergent or divergent in general. And so the reason why we use the word convergent and divergent is because ultimately we're dealing with limits, right? Improper integrals are limits. So that same terminology of convergent and divergent relates the same. So if you recall, an integral or a limit is divergent under two conditions, really. One of them is that it becomes unbounded. It shoots off to positive infinity or negative infinity. The second case is that it doesn't actually converge, so maybe it oscillates. So think like a sine function. If I take the sine function all the way to infinity, it always is doing this. So it never actually settles down to a point. So that limit also diverges because it doesn't squeeze down to a point. It doesn't approach anything. It always is just oscillating. So those are usually your cases. They either don't exist because they don't ever settle down, or they might exist but they're not finite. They just shoot off. So we consider both of those cases divergent limits. So anyway, the first case is we have 15 over x squared from 1 to 10. Now, what I notice here is actually this is not an improper integral. I look at this and I say, oh, well, this isn't improper. So one thing I want you to, the reason I want to point this out is that don't always go into anything being like, oh, it's got to be improper. It doesn't have to be improper. You can look at something and go, oh, okay, that's just a standard integral. Sometimes, too often when we learn these new techniques, we're like a hammer looking for a nail. And that's not appropriate. If you look at, again, the graph of 1 over x squared, it's continuous for all positive numbers. So as long as this isn't a 0 and that's not an infinity, then it's not an improper integral. So you just simply take the antiderivative you get 135 over 10, which I guess would then still reduce if we wanted to, right? We could take a 5 out of it and get like, what, 27 over 2 or something like that. Doesn't matter. Anyway, that's the idea. So, again, don't always assume it's going to be improper just because you're used to doing improper integrals. The next one is this 1 over x dx. Okay. 1 over x dx. Well, if I take I look at this and I say, oh, okay, it's got an infinity there. It's got to be an improper integral. And the answer is yes, it is. So we have to rewrite this. We have to say, okay, well, that's the limit as b goes to infinity of 1 to b of 1 over x dx. And it's kind of cumbersome. I get it. You know, we don't like writing extra pieces, but that's just part of the process. And luckily, when you get used to this, as you take more and more math classes along, you stop having to do this. You can kind of go straight to here, and people expect that you know that this is really happening underneath. It's actually really convenient. So if we keep on going, we say, okay, well, what's the antiderivative of 1 over x? So we say, okay, well, hopefully you remember this, but you may not. And the antiderivative is that it's natural log of x, and we're going from 1 to b. So now we need to plug in the limits of integration here. Natural log of b minus natural log of 1. And hopefully you remember that natural log of 1 is always 0. And even if you didn't, hopefully you remember the log rule that says if they're subtracted, you can take this divided by that. Well, b divided by 1 is just b. So it's the same as just that one disappearing. So we end up with the limit as b goes to infinity of natural log of b. So to do this, I have to think a little bit about how the natural log works. And the natural log is, the graph of the natural log looks like this. I mean, it's not perfect. It goes through 1, 0, it goes down to negative infinity here and then shoots off to positive infinity. So the limit is as b goes to infinity of natural log, it shoots off to infinity. So what I end up with is infinity. So this is so this diverges. So we would say this is a divergent integral. But the idea is we could get all the way here, but the limit wasn't finite, so it's considered a divergent integral. Now I want to jump to here next. I don't want to go to here, but we'll get there. But I want to jump to here next because there's really three cases for this. This is 1 over x to the p, and this is a very important integral for dealing with infinite series, which you'll eventually get to. And so we really want to take a look at this. So 1 over x to the p. Well, there's really three cases. There's case 1. Where p equals 1. So this is just 1 over x to the 1. Well, that's this. So we know that diverges. So it doesn't matter. Okay. Now, there's case 2. And case 2 is this idea of p being greater than 1. So p is greater than 1. Well, let's talk about p being greater than 1 for a second. So if p is greater than 1, then that integral is x to the negative p dx. Right? That's it's the same. It's going to be the same for the other case too. The case where p equals 1 is special because it's a natural log. Everything else we can use the power rule for. So then what we do is we add 1 to the power, and then we divide by that power. What 1 to be? Now, here's the real kicker. If p is greater than 1, if p is larger than 1, then 1 minus p is actually negative. Does that make sense? Like, for instance, if p was 2, 1 minus p would be negative 1. If p was 1.5, it'd be negative 0.5. If it was 1.10001, right, it'd be that 0.001. So what we can do is we can say, well, that's the limit as b goes to infinity of 1 over 1 minus p times 1 over x to the negative absolute, x to the absolute value of 1 minus p. Or probably better to write it as p minus 1. From 1 to b. Now, why am I saying that? I'm saying that because then I can plug in b here. I can say that's the limit as b goes to infinity, 1 over 1 minus p, 1 over x to the absolute value of b minus 1 minus, it's just 1 when we plug it in. So why am I saying this? Well, as b gets larger, right, 1 over x gets really small because x to the power grows and grows and grows. So this actually shrinks down to 0. And this was negative, right? Remember we said 1 minus p is a negative number. So this goes to 0. This comes here. So we get 1 over p minus 1. But p is just some fixed number, right? It's some fixed number larger than 1. So this is a perfectly fine, this is just some number. It's 1 over p minus 1. That tells us that this converges. Now what about case 3? What about the case where p is less than 1? Now if p is less than 1, now we still have this, but this we have to rewrite. Because if it's less than 1, we still have this integral. We still can apply the power rule. We get this limit. I'll kind of snake that off here. You end up with 1 over 1 minus p. Now, notice that 1 over 1 minus p is now positive. 1 minus p is positive. So instead of this, I have this. Now, I still get that minus 1 when I plug in, because x to any, or 1 to any power is just 1. So don't worry about this little 1 here. But instead of it being on the bottom, it's on the top. Or the power's in the top because the power wasn't negative, the power was positive. So now I'm taking this limit here. Well, if x is to a positive power and x gets really large, it just shoots off to infinity. So this actually diverges. So what you find is that if p is greater than 1, this always converges, just straight up. So if you see something like this, if it's x squared, x cubed, if it's x to the 1.01 on the bottom here, always converges. Always converges. Now what it converges to is a different number. But if you find that it's 1 over x, or if it's like 1 over x to the 1/2 or something like that, nope, diverges every time. So we don't actually have to, so what's nice about this is what's called a p-series. Well, it'll be called a p-series when you get to the summation piece, the sequences and series section. But this is a very, very important integral that has a lot of applications in different areas, I guess, for lack of a better word, of stability theory, trying to figure out if something converges or not. Anyway, so that's a really important one. So we'll circle back to that as needed. Now, this is clearly an improper integral because we have an infinite limit here. So we need to take the antiderivative. Now, hopefully you can figure out that the antiderivative here is negative e to the negative x, and that this is the limit as b approaches infinity of 0 to b e to the negative x dx. So this is the limit as b goes to infinity from 0 to b here. So when I plug in, I get the limit as b goes to infinity of negative e to the negative b plus 1. So you end up with a plus 1 because you're subtracting negative e to the negative x. So it's really plus e to the 0, when e to the 0 is 1. So you have this piece here. Well, as b gets very large, you can think of it as like e to the negative infinity, which is like 1 over e to the infinity. Well, that's a huge number, right? So 1 over a huge number is 0. So the answer is 1, and it converges. So that's kind of an important piece. And finally, we want to take a look at this integral, x e to the x dx. Now, the reason why this is kind of is interesting one is because we have infinite limits on both sides. So the way that you deal with this is by setting up some intermediate point. So what we do is we say, okay, this is the limit as a goes to negative infinity from a And you can pick any point you want, but I often it's a good idea to pick 0, but you don't have to. You could pick like 3 or 10 or negative pi, who cares? But it has to be consistent. So I have to say to 0 x e to the x dx plus the limit as b goes to positive infinity, 0 to b x e to the x dx. So just make sure that whatever you pick here, you have to pick that there. Otherwise it doesn't work out. Like you're cutting it the wrong way. You're trying to cut it in the middle and examine two integrals separately. So, and you may not remember this, but the antiderivative of x e to the x dx, well, I say remember, you apply integration by parts. And if you apply integration by parts, what you get is x e to the x minus e to the x. Again, I don't know if you remember that, or I don't remember. Hopefully you are comfortable enough with integration by parts that you could have gotten that yourself. And you can check this with differentiation, that this all kind of comes out. So now we have the limit as a goes to negative infinity plus the limit as b goes to positive infinity from 0 to b. So what's nice about this is when I plug in 0 here, you know, this term vanishes and that term becomes a minus 1, so, or a positive 1 rather. So I end up with the limit as a goes to negative infinity of a e to the a minus e to the a plus 1. And then I have to add the limit as b goes to infinity of b e to the b minus e to the b plus 1. So these are two separate limits. You evaluate them independently. Now, ran out of board space, so I'm having a little trouble. Now, what you're going to do here is you're going to apply L'Hopital's rule. The easiest way to do this is to group this together. So I'm going to look at this particular limit. I'm going to say this is the limit as a goes. Now notice that these ones don't matter. So at the end of the day, this is, I'm not going to worry about those plus ones. They matter insofar that if you're trying to solve for what the integral is, we have to keep up with them, but they don't affect the limit here. So if I take the limit as a goes to negative infinity, I can break that out as e to the a times a minus 1. Okay, so the reason why I want to do that is then I can, instead of writing it that way, I can write that as e to the negative a. So why would I want to do that? Well, the reason I want to write it that way is because if I plug in the infinity here, I get an infinity on top, and then the negatives cancel, so I get an infinity over infinity case. So then I can apply L'Hopital's rule to get the limit as a goes to negative infinity of 1 over negative e to the negative a. Well, then when I do that again, I get 1 over negative e to a big number, right? So because those negatives cancel, so it's like 1 over e to a huge number. So that means that goes to 0. But I have to do the same thing for b, but it's the same exact process. It's the same process. I say the limit as b goes to infinity of b minus 1 e to the b. Now this one you don't have to worry about. So again, we're here. We don't have to rewrite it in some convenient way. Because if you plug in positive infinity here, this goes to infinity, that also goes to infinity. So it doesn't matter. You get a positive infinity there, which means that this limit diverges. So I apologize, we ran out of space for me to really do this justice. But the whole point on this is that this half, that sort of negative half, that was a convergent integral. That, if you do yourself a favor, go take that function there and graph it. Go, plug it into some sort of graphing calculator. What you'll see is something that looks kind of like this. I can't quite remember, but it strips off. It's always like negative there, but it strips off and rides the tail here, and I think it has a little bump. And then goes straight through the origin, and then just shoots way off to infinity. So this strip is actually finite. That strip isn't. So I'm a little worried because that shouldn't be +1. Like here, you should actually get like some sort of negative. This should almost be like a -1. I'm not really sure why that happened. It doesn't matter because that's not the teaching point. The teaching point is that even though this half converged, this half very much diverged. And since it diverged, there's it doesn't matter. The whole thing diverges. If one thing tips it over, tips the whole thing over.